So I don't know how many of you have deployed and developed distributed systems, but I've done a fair bit of that over the past decade or so, and I can tell you that my experience with creating such systems is it's not great. It's not great, and the reason why it's not great is that I think that we don't do it in our programming languages. So the stuff that we write in our programming language really just describes what one OS process is doing generally. And then the deployment is described out of band by some other tech, like, I don't know, CloudFormation templates and YAML files and stuff. And the build deploy cycle is then managed by yet more tech. And none of this stuff is in your programming language. Now, in Unison, we do things a little bit differently, where a program can describe an entire distributed system. And, instead of having this sort of deployment technology, you just run the program to deploy it. And, there's no build deploy cycle because we don't have builds. And the deployment of the system is just written in Unison. And we call this just-in-time deployment. So I'm not going to go into too much detail about how that works, but I'm just going to kind of contrast that with how traditional systems are made. So most distributed systems today, they use either message passing or remote procedure calls, which I guess has kind of fallen out of fashion, or some kind of event bus. And so in RPC and message passing, everything has to sort of agree on something. Like with RPC, all the locations have to have the same code, or must agree on the code. In message passing, the services have to agree on some protocol that you have to then exchange messages written in that protocol. With an event bus, also, you have to agree on the data format that goes on the bus. And so this is sort of a coordination problem. Now, in Unison, we replace, there is a shared data format, but that data format is Unison. And so every node on the network, on the sort of Unison web, is running Unison. And then nodes, instead of sending data or whatever, they send hashes. And you communicate with another node by saying, okay, execute this hash. And the other node may have that hash already. And if it doesn't, we deploy the hash to the node and then execute it. So just-in-time deployment. So we send the Unison code when necessary, and we send all dependencies if possible, or up to a particular depth. So so in Unison, since the code base is structured and every Unison object has an unambiguous hash, we can write programs that distribute themselves to remote locations. So we want to show you a little bit of code, like how that works at a high level, just like what your code looks like. So this is a map reduce or a fold on a tree-like data structure. So it has three cases. It can be empty, it can have one element in it, or it can have two branches. So it's more stuff down the left and right branch. And so this is a traditional sort of fold over that structure where we have some operation that I'm calling map op, which I want to execute on every element in the tree. And then I have Z, which is some base case. And then I have bin op, which is a binary operator that I want to use to sort of reduce the stuff that I've computed using my map op. All right, traditional sort of map reduce. And this proceeds recursively. And this is the kind of thing that would just run on a single process in a single thread. There's no concurrency or distributed stuff going on here. But the thing I want to show you is what happens when you take this to a distributed system. So traditionally, you want to take a program like this and you say, okay, now run the distributed version of this. And today, usually the answer is like, okay, well, you got to read up on Hadoop and Spark. And so we move away from the nice world of like 7 lines of code that any programmer could write in 10 minutes to like huge multi-million line frameworks that have like 600 plus page books and like entire industries dedicated specifically to figuring out how to take those 7 lines of code from the previous slide and like make them distributed. So in Unison, the change is really just going to be very small. So it's going to be kind of like that. And you may not even have noticed that this was very much different. So then this is now going to be a distributed MapReduce on a tree-like data structure. And so all I've done is add this call to fork. And I've added this sort of tick to the expression that I'm passing to fork, and put it in parentheses. So fork means get a nearby Unison node from a node pool, and that node pool is going to be provided by a handler outside the program. So just to very cursorily give you an idea of how that works is that fork actually throws an exception to something that's outside of your program, so it gets handled and it gets given a node somehow, and then the exception handler transfers control back to the program. But as a programmer, as just a user of a library, you don't actually see that happening. So you just call fork, and I give it this closure. So I'm putting this sort of tick and put the expression in parentheses, and that means don't evaluate this expression right now. Pass it unevaluated to fork. And what fork will do is it will hash it, and it will send the hash to Unison node that it got, and ask that node to execute it. So if that node has not seen that hash before, we ship the code and all of its dependencies to the node. So that's at a high level how distributed systems or what distributed programming is going to be like, going to feel like in Unison. Another thing I wanted to touch on is that Unison documentation is written in Unison. So one of the things that we do a lot of as programmers that we don't use our programming languages for is writing documentation. So there's always some kind of external language, I guess, unless you're writing a Lisp or something, but in like Java and Scala and Haskell, and there's always some kind of like doc language that you use to write documentation in. In Unison, documentation is just written in Unison. So you can precede a definition with a sort of a doc block. So you put this in sort of double curly braces, and then you put documentation inside of that. So here's a definition. It's a function that takes no arguments, which I'm calling my constant. The definition is 41 plus 1. And I'm documenting that, saying it's an important constant. And Unison will associate the documentation with that definition in the code base. And if I desugar that a little, that's just saying there's another definition called my constant.doc, and that has type doc. And its definition is, this sort of documentation expression, which is also just syntactic sugar for some more complicated Unison expression. And this is all going to be, it's all in the language reference, how to use this stuff. But we can do other cool stuff, like we can evaluate expressions inside of docs. So we can put Unison expressions inside of a doc. So here I've put, evaluate my constant. So an important constant whose value is whatever the value of my constant is. And then rendered, it will actually evaluate that expression. And you can put links to other documents or any Unison definition in your documentation. So here, I'm saying my constant has value 42 and is of type nat. So nat is the type of natural numbers. So 42 is a natural number in Unison. And so my constant, in the rendered version of this, my constant here will be a hyperlink to the definition of my constant, and nat will be a hyperlink to the definition of the natural number. All right. So the documentation type provides a rich vocabulary of elements. So I've only really sort of touched on it, but it's very similar to Markdown. There's a Markdown-like syntax, but it goes well beyond Markdown. It has headings and callouts and block quotes and tooltips and tables and cool stuff. And we can include Unison code, and that code is type checked, and optionally you can evaluate that code. Hyperlinks so links to other docs or links to definitions are unbreakable. That is, they use the hash. So if you move something around, the link will still work. If you rename something, the doc will be automatically updated in the sense that, the name of the hash in the code base will just change. And importantly, docs are just Unison objects. So you can assemble documents programmatically in Unison. And so you can write Unison expressions that generate docs. So just taking a step back, I want you to think of the big picture here, like what's possible with this kind of thing. So this sort of first-class computable document format presents the possibility of a radically ergonomic way of interacting with both code and documentation. So you can just imagine, like, if the code base is one big hypermedia wiki with bidirectional links that are type checked and unbreakable, and you can put code or link to code anywhere in a document. It's like Smalltalk and Jupyter notebooks and a wiki, like all in one. So we're really only scratching the surface of what we can really do with this. All right. So now I really want to give you a quick demo of like what it's like to program in Unison. And this may all go really badly, so we'll see. We'll see how that goes. So here I've started up my Unison Codebase Manager. And so I have, okay. So this is running the latest development version of Unison. So this is not the latest release, but this is trunk, like the stuff I was working on today. And so the documentation format that I was just showing you is in this, and that's coming in a release very soon, which we're calling M2, which we're hoping to a milestone release 2, which we're hoping to release very soon. But just to show you how the workflow in Unison kind of works right now. So when I start up my Unison Codebase Manager, which installed, you would type UCM at the command line, but I'm running Haskell stack here, so I'm saying stack exec Unison. And so this is all running sort of unoptimized and everything. So bear with me here. But if I follow this link here, so Unison Codebase UI is running at this place here, I follow that link. And so we have this sort of beginnings of kind of like a browser for the code base, like a graphical browser. So I have like my base libraries here. And we can go into something like a definition of something like, oh, what's here? Maps, great. So fold left on map. Let's find the function fold left or map on them. Great. So it'll show me the definition of map on map. So that will take a function from A to B, which has some effect E. I'm not going to go into Unison's effect system, but we're using a system of algebraic effects, which we're calling abilities, which is interesting in its own right. But so this map takes a function from A to B. It takes a map with keys of type K and values of type A, and it turns it into a map with values of type B, right? And so what is this map with key? And we can click it and we can see what's the definition of that. And then, on we go. We can get what is the definition of map. So this is the map type. So we can sort of follow hyperlinks in this thing. And it has this sort of find feature as well. So I want to find sat map maybe. set flat map, and then it'll show me that. So this is the sort of beginnings of an IDE or a graphical interface for the Unison code base. So that's kind of awesome. So normally, I would have this sort of to the left, and then or like in the corner when I'm working with this. But I have my fonts pretty big here. So what I have here is the Unison Codebase Manager running in my terminal, and it tells me that it's watching for changes to .u files under this directory. And here I have a file called scratch.u in my directory. And so that's where I'm going to put all the code that I'm working on. And it turns out that you can just have one file. You don't have to have a directory full of Unison files that you then submit to a compiler or whatever. I can do all of my work in just one file. And typically it turns out that I in fact do just that. So let me show you just how it's going to work. So I can put a greater than sign at the beginning of a line, and then I can put an expression on that line, say 42 plus 3. And if I save that, the Unison Codebase Manager comes back with the evaluated form of that expression. So this is called a watch expression. And I can put any Unison expression in here, and it'll just evaluate it. So what I usually do is that I put this sort of triple dash. So anything below a triple dash of this triple dash thing is called the fold. And so any line that has 3 or more dashes at the beginning, anything below that will be ignored by UCM. So I end up having this sort of stack of stuff that I've been working on, and it all just kind of gets pushed down. And so and I'm like, okay, I'm kind of done working with this thing right now. And so I just add this sort of line. I have a hotkey to add that in my VI. And then I can start working on something else. So for example, we could write the definition of some function. So let's see if we wanted to, for instance, write head on a list, say. So let's write that. So head would take a list of A, and it would maybe give me an A, or optionally give me an A. And you might be asking, oh, is it called optional or is it called maybe? It's called both, actually. In my code base, it's called both maybe and optional and option, because I can never remember which one is which. And Unison can just allow me to have all of those names, and I can use them interchangeably. So then I can say, maybe we can get this done. So head of the equals cases. So if it's empty, then we do none. And if it is not empty, that is like that. So if it's some element of type A, there's some element A followed by anything, then we return some A. Hopefully that works. Okay, that works. So I said I found and type checked this definition. And now it's saying this is now ready to add. So it's ready to be added to my code base. It actually tells me that this already exists. It's called base list head. So it already exists in my code base. We can, well, we can just say identity of some A. So now it definitely doesn't exist. Just calling the no-op function on this. And then I can go into like a namespace and call this YOW. So now I'm in a namespace, empty namespace YOW, and I would just want to say add. So then it says I've added these definitions, and it added some metadata for me. Let's say metadata head. No, wait, what is it? It's not metadata. Wait, is there anything in here? Yeah. U1. I've actually forgotten how to use this. metadata list. Is it links? It's links. Links head. So I just use the help in order to figure out how to use this tool that I'm developing. So if I say links of head, it'll tell me that it added this sort of metadata. So the author is me, and it added a license, which is the MIT license, copyright Unison computing. So it did that for me sort of automatically. But importantly, this is now in my code base. And I've added this definition, and I can now actually just get rid of the source code if I want, and it's gone. And I can always get it back. I can say edit head, and there it is. Reloaded it, and it automatically adds a fold below it. So one thing you might notice is that I didn't do any imports. There are no import statements here. And that's another thing that Unison, we don't find import statements delightful, and so we got rid of them. No, you can do imports, but you don't have to in most cases. So the reason why this doesn't have any imports is that, for instance, optional is unambiguous. So I only have one type named optional in my code base. It's actually called base.optional, I think. Yes, base.optional. But I only have one such name. And so this is actually an unambiguous name, and it's totally fine. Same with id or ID and some and none. Like none of this stuff I had to import. So that's really fun. And we do lots of cool tricks to try to not have you have to do imports. Like we try to, you can use the shortest, the longest, what is it? No, any unambiguous suffix you can use to of the name to reference something. And even if you do use an ambiguous name, we will still try to figure out what the right one is by type checking it. And then if there's only one thing that type checks, we will just use that. And so that's another cool facility here. And now you may be asking, like, okay, well, what if I want to edit this stuff here? So editing is, I just change this, and I can now say update. And now I've updated this definition in my code base. And so what I've actually done is just add the new definition, and I've reassigned the name head to the new definition. So the code base is sort of append only, and the history of the whole thing is stored. And so before I did update, there's a hash for the whole YOW namespace here. And so I updated head, but I could go back to before that. And so we never actually destructively update anything. So the only thing that happened when I did update was that I reassigned the name to this other thing. But I also, I believe, made a patch. So it automatically keeps track of changes in this thing called a patch. And then you can apply the patch if you want to make the same changes somewhere else. So we intend to make pretty nice facilities for editing patches so that you can sort of have very controlled updates to your libraries and things like that. So yeah, I think that's basically it. Like that's how you interact with Unison. Another thing I kind of wanted to show you, that you can ask for the type of anything. You can say, oh yeah, so view has the, head. The code base knows the type or head here, so it shows you the type of whatever you have. But you can also find things by type. So if I want to say find something of type A to maybe A, like that, it tells me all of the things that have that type in my code base. So that's pretty cool. And yeah, with that, I think I'm going to leave that here and go back to my summary here. So as of now, we have this imminent milestone release called M2, which contains a faster runtime. It has a visual codebase browser that I showed you. We have this new relational codebase format, which is like 100 times faster than the previous format, or 100 times smaller, at least, up to 100 times smaller than the previous format. We have this improved documentation type that has a very rich language for writing documentation in Unison. And we're ready for enthusiasts to write and share libraries. So come join us in the Slack, in the Unison Slack. I'll give a link to that here at the end. In the next few months, the roadmap is to have an open beta, so open to everybody. Right now, you have to sign into the Slack to get the UCM. And we're going to squash bugs. We're going to write more libraries. We have a basic cloud computing API in the works. And then also whatever it is that you decide to do. This is now, it's a new language. There's not a lot of stuff already implemented in it. And so you could have a significant impact on the way that this language develops in the future. So yeah, there's nothing left to do other than just to start coding. As if you go to unisonlang.org, you can download and install and come join us. Thank you.